What's up?
Just out of curiosity,
Mhm.
since there's a rocket team, would you wear the shirt we're trying to make?
Would I wear this shirt?
Yeah, it would be a long sleeve. And that would be the back.
Did that get approved by? It's a little bit too much bread, if you know.
What would you consider it? Just,
I would consider it,
yeah, okay.
but make sure it gets approved by by the right people first.
Oh, I talked to them.
This, me being over here is actually, yeah, I just, cooties and stuff, you know, I gotta get away. I mentioned a girl that's in a Discord, my girlfriend got something, so I'm gonna be over here. That's a real thing, by the way. I mentioned, when I mentioned Carney in the Discord kind of thing, and she just shut down. I'm like, you're joking, dude.
What's up?
Trunking or
Truncate, yeah, truncation.
That's these nonsense here. Here you
I'll put up here. Sorry. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Doing good, doing good. All right. All right, so we're in week 3, and so we're getting into now that we're kind of done with I would say most of the review for this course. So we did a little bit of heat transfer, fluid mechanics review. Last week we focused mostly on MATLAB review. Now we're actually getting into the class itself. Okay. And so today, I think we started a little bit last time. We started talking about finite differences a bit, so we're going to expand on that a bit more. Talk about what finite differences actually means in terms of how we actually use it. We're going to talk about errors, truncation errors, and then by the end of the day, I'm hoping that we can actually start applying this to solving some differential equations. Okay. All right, and so announcements. Remember, homework 1 is due tonight. So homework 1 is mostly the MATLAB problems. So make sure you guys are doing that. If you have any last minute questions on it, I'll be available just for a little bit after class. I do have to teach another class after this, but if you send me an email and it gets to me and I read it before I go home for the day, then I'll try my best to help you out. Okay. All right, and so that's it for my announcements. Are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. And so last time we were here, we were talking about finite differences. So, like I mentioned last time, the first half of the course, we're going to be focusing on finite differences. The second half of the course, we focus on finite volumes. And so, the idea with finite differences is that, we want to take derivative expressions, and so kind of mathematical expressions for derivatives, and turn them into algebraic expressions. Okay? The finite difference isn't the only technique for this. We are going to be going over finite volumes, and finite elements is kind of the same too. So they all kind of have the same goal. It's to turn differential equations or systems that are governed by really complicated equations and turn them into algebra. Okay, and the reason for this is that algebra has the advantage that computers are really good at solving algebra. You can write computer algorithms that can solve algebra problems really well. Okay? And so basically the whole branch or big branch of just computational science in general is how can you turn stuff into algebra problems. Okay. Okay. And so last time we talked about finite differences. And so, finite differences is based on just this very simple idea of, how do we take the slope of a curve, right? And so I think last time we were looking at a curve like this. And so let's say that we know the data points in this curve, okay? 1, 2, 3, 4, 5, 6, 7, 8, and 9, okay? And so if we wanted to take or compute the slope around 0.5, and we had information about the data points, we simply just would compute the rise over run in that vicinity. Okay. And so slope would be the rise over the run, okay, where the rise is the difference in the y coordinates. Y coordinates in this case would be the difference between y6 and y4. And the run would be the difference in x coordinates in the surrounding nodes as well. And so it would be x6 minus x. All right. And this is good because if we said that this curve here represents a function y of x, then this algebraic expression for the slope would be exactly dy dx in the neighborhood of x is equal to x. Okay, that's the basic idea of finite difference. So you basically take a derivative, you compute rise over run. That is your thing. Okay. All right. And so for the types of problems that we're going to be doing, we're going to often make the assumption that the space, the horizontal space between data points is uniform. And so this distance between x1, x2 is the same as this distance between x2 and x3, okay? And oftentimes we call this delta x, okay? So delta x is often what we call the grid spacing. So grid spacing is just the distance or the length in between data points. In the horizontal direction. And we're going to assume that this is uniform. Okay. It doesn't have to be uniform, and so there are definitely cases where you're going to have a non-uniform mesh. These will be cases when you have kind of mesh refinement in an area of maybe high stress or something like that. But as we're developing the theory, it's kind of useful to assume a uniform grid spacing. Okay. And so if we make this assumption, then our finite difference approximation for the derivative becomes simplified a little bit, because instead of x6 minus x4, what we can do is we can represent this as a function of the grid spacing. And so our dy dx in the neighborhood of x is equal to x5 is equal to y6 minus y4, all divided by 2 delta x. we can generalize this even further too, right? Because, you know, this expression here is the derivative in the neighborhood of x is equal to x5, but there's no reason why we couldn't use the same expression for almost anywhere else in the grid, okay? Say that dy dx at x is equal to xi, where I'm using the subscript I here to denote basically any location on the grid or any location in the domain. You know, this is equal to y I plus 1 minus y I minus 1, all divided by 2 delta x. This one's going to be useful for us, and we're going to use this one a lot. And so this is what I call the central difference scheme. Central difference scheme for the first order derivative. All right, any questions on this so far? Yeah.
I don't understand the 2 delta x.
Yeah, good question. So I used 2 delta x here because we kind of spanned over 2 grid spaces, and so you know we're looking in the neighborhood of 5 right here, and so the distance between 0.4 and 0.5 is delta x, and the distance between 0.5 and 0.6 is delta x. Yeah, yeah. So we kind of took one neighbor to the left, one neighbor to the right, so overall it's 2 delta x. Yeah, good question. But that kind of brings me to my next point too. And so, you know, that's one way we can look at the derivative, right? We can look at one neighbor to the left, one neighbor to the right. But actually after class on Wednesday, people asked, you know, can we use this same scheme? So, you know, what if we wanted to find the derivative around 0.1 or maybe 0.9, right? The problem with these points is that, you know, we don't have neighbors on each side, right? These are endpoints. And so for the case of 0.9 doesn't have a neighbor on the right. Okay. I know the way I kind of drew the curve, it kind of looks like it's going, but let's just assume that 0.9 here is an endpoint. Okay. And 0.1 here has no neighbor on the left. And so if we were to try to apply the central difference scheme, we wouldn't be able to apply it because we don't have, you know, those neighbors. Okay. But what we can do is we can come up with modified versions of the central difference scheme to account for these kind of n pieces. Okay. And that kind of gives rise to two more finite difference schemes that we can use for the derivative. So there's 2 more we can do. And so one of them is called the forward difference scheme. And so for the forward difference scheme, we have dy dx at x is equal to xi. This is equal to yi plus 1 minus yi, all divided by delta x. And then we have the backward difference scheme too. So dy dx at x is equal to xi, this could be yi minus yi minus 1, all divided by delta x. And so the nice thing about these is that they do rely on a neighbor, but you only need to have one neighboring node, basically, right? And so if you can imagine, for point, for node 1 here, right? And so for node 1 has no left neighbor, but it does have a right neighbor, right? So it has a neighbor on the right, which is 2. Okay? So we can apply this at node 1. And the backward difference scheme, if we look at the other side of the domain, node 9 doesn't have a neighbor on the right, but it does have a neighbor on the left, right? And so we can apply this backward difference scheme to the right side of the domain. Okay? And so here we have kind of our 3 finite difference schemes here for computing derivatives. So this kind of, begs the question a little bit, right? So we have these 3 schemes, okay? We can see different cases where we'd use one over the other, depending on where we are in the domain. But besides that, it kind of begs the question of, why would we choose one over the other, right? So, it kind of almost seems like the central difference scheme has the strictest requirement because it has to have a left and right neighbor, right? And so why would we use that over the other ones? Well, the answer to that has to do with accuracy. Okay? And in fact, it'll kind of segue into our next topic, which is truncation error. Okay?
Bless you.
All right. And so, before I kind of launch into this idea of truncation error, I want to kind of remind you that, when we use finite differences like this, it's not a magic pill, okay? And so by replacing a derivative expression with an algebraic one, we're making assumptions here, right? So, this expression for the derivative is not going to give you an exact solution. There's going to be some error involved, right? So never. So that's kind of an important thing to remember, is that finite differences is just an approximation. It's not an exact representation of the derivative. We're just approximating, okay? And whenever you start talking about approximations, that means there's always going to be a difference between what you compute with approximation versus what it is exactly, okay? In other words, we can say that there's going to be errors involved. Okay? A lot of times these errors are going to be really small and they're not going to be noticeable, but there are going to be errors. Okay. What we can begin to do is we can use this ideas of errors to talk about which scheme that we've talked about so far is going to be the most accurate or has the least amount of errors. Okay. And so to talk about this, we need to bring back probably something that you hope you would never ever see again for the rest of your life, and that's the idea of a Taylor series. It's only for today, I promise. We're not going to look at it again. And so the Taylor series actually gives us a good way to quantify what the errors are in these finite difference schemes. Okay. So for example, let's apply the Taylor series to the forward difference scheme. What we hope to obtain from this exercise is basically an expression of how the error is going to change with the 4 different schemes. Okay. All right. So let's go ahead and write the derivative here. So with the 4 different scheme, we know that it's yi plus 1 minus yi all divided by delta x. Okay. Another way that we can express this is we can say that this is going to be equal to y x plus delta x minus y at x all divided by delta x. Okay, that's kind of another way to express the the finite difference. And then what we can do from here is we can keep adding the Taylor series terms that come after that. Okay. Okay. And so after this, the Taylor series expansion is, so we're going to have a second order derivative term. So you have d squared y dx squared times delta x over 2, okay, plus d cubed y dx cubed delta x squared over 6, okay? And it kind of continues on from there. Okay. Well, I skipped a few steps to get here, but it's not that important. I mostly just wanted to show you the result, and I kind of wanted to tell you kind of where I got this. So I'm not pulling this equation out of my ass, but it kind of seems like I kind of did anyway. But if you kind of work through the Taylor series expansion of y of x at delta plus delta x, and you kind of work your way to the derivative, then you're going to end up with this expression. Okay. So after. But there's not a class on Taylor series, and so we're not going to dive into the details. Okay. So there are some things I want to highlight from this equation. So on the left hand side here, we obviously have our derivative. This one is 2, right? And so these two things that I've kind of highlighted, they're the same thing. And so the next two things that come in our equation here, this is our forward difference approximation. Okay. So in fact, let me kind of erase one of these just so it's clear. Okay. And so right now, that's all that we have, right? And so what we set up there was that the derivative was equal to our forward difference approximation. Okay. But if you actually expanded this with the Taylor series, you would see that there's actually a lot of other stuff that's involved as well. Okay. So all of these terms over here, okay, these are the error terms, right? And so when we make our forward difference approximation, the error or the things that we're missing out on is everything else in the Taylor series. Okay, so this is our error approximating. Yeah, question.
So is this just kind of related to why we use the central difference because it's not going to have as many errors come along with it?
That is, yes, that is going to be the conclusion that we'll reach in about 15 minutes. But yes. Yeah, question.
The delta x involved with this Taylor series, is that the same as the grid space?
It is. It's exactly the same. Yeah. And then so what we're going to see, so the way we're going to characterize these methods is how the error scales with the grid spacing. Yeah. That's how we're going to characterize it. And so, of course, the Taylor series continues on until infinity, right? And so one way that you can see is that we're missing out on infinity number of terms. And you would be right. But the nice thing about this is that if you'll notice that all these terms, they scale with the grid spacing, right? And so if you look at each of the terms in the Taylor series, you're going to have a delta x squared, delta x cubed, and it's going to continue on like that, okay? And so usually when we're doing these computational methods, we usually choose the grid space in such that it's pretty small, right? And so it's going to be something that's less than 1. Okay. So it's usually somewhere between 0 and 1. Okay. And the nice thing about this is that when you take a decimal or you take a fraction and you square it, what happens to it? It becomes smaller, right? And so what that means is that the most significant error term is actually the first one. Okay? And so this term right here, this is going to be the most of the error is going to be in this term. And so we often call this the leading error term. And so you'll hear that terminology a lot if you look into the literature on computational methods. And so people always ask, what's the leading error term for this method? Okay. And so what we say is that, to characterize the method, so to characterize a method, finite difference, finite volume, finite element, whatever, the way that's often done is that you look at the leading error term and you look and see how it scales with the grid spacing. And in fact, most of the time we actually ignore any fractions too. So even though in this Taylor series expansion we have delta x over 2, we kind of ignore the over 2. And so the only thing we really care about is just the power of delta x. Okay. And so for the forward difference scheme, so the forward difference scheme are our leading error term scales with delta x. Okay. In other words, it scales with delta x to the first power. So what we say is that this method, this forward difference method, is first order accurate. All right, so what we're going to do, so we're going to repeat this process for the backward difference. Maybe I will show you the Taylor series just so it's, just so it's not magic. And then, we'll show you that, I'll show you that, when we do the same procedure for the central difference, we actually end up with the method that's second order accurate, which tells us that central difference is going to be more accurate than the other ones. All right, any questions on this so far? Okay, all right, so let's do the same thing. Let's apply it to the backward difference scheme. Okay. All right, so for the backward difference schemes, let's take a Taylor series approximation around y I minus 1. Right, so we have y I minus 1. And so I'm going to take a Taylor series of y I minus 1 centered around yi. Okay. Okay. And so y I minus 1, this is equal to y at x minus delta x. And if we take a Taylor series approximation around y of x, then what we say this is equal to y of x minus dy dx delta x plus d squared y dx squared delta x squared minus d cubed y dx cubed delta x cubed over 6. Over 2. Sorry, forgot those terms. Okay. And so let's take this expression and let's solve for, let's rearrange this algebraically to get our backward difference scheme. Okay. So this, what I have up here right now, that's the straight up just Taylor series approximation of y x minus delta x. And so here I'm just going to rearrange things up a little bit. Okay. So I'm going to take this y of x, I'm going to move it to the other side of the equation here. Okay. We have y x minus delta x minus y of x. And then to get the backward difference, I'm going to divide everything by minus delta x. So we divide by minus delta x. Okay. So this is equal to dy dx minus d squared y dx squared delta x over 2 plus d cubed y dx cubed delta x squared divided by 6. Okay. Okay. All right, so I'm going to take this minus sign here. I'm going to apply it up top, just so that we get the straight up backward difference scheme there. Okay, so we have y of x minus y of x minus delta x divided by delta x is equal to dy dx minus d squared y dx squared delta x over 2 plus e cubed y with dx cubed delta x squared over 6. All right, so I'm going to stop it here. And so what I've boxed in pink right there, this is our backward difference scheme, right? So our backward difference scheme says that dy dx, which is our derivative, is equal to the left, our current position minus our left neighbor, all divided by the grid spacing. Okay. And so if that's our backward difference scheme, then everything else is going to be error terms. And in particular, remember, we're interested in the leading error term. So the first error term that appears, because that one has the lowest power of delta x. And so we can see that this leading error term has a power of 1 to the delta x. Okay. And so what this tells us is that the backward difference scheme, very similar to the forward difference scheme, is also first order accurate. All right. Any questions on this? All right, so both forward difference scheme and backward difference scheme are first order accurate. Okay. First order accurate is not bad. It's better than being not accurate, right? So the fact that we actually get a legitimate, first order error term means that these are at least legitimate methods. Okay. Usually, practically speaking, when you're using a method, most of the time you're going to want to use a method that's at least second order accurate. But first order is not bad. It's better than an illegitimate method. And so, of course, that leaves our last method to examine here, which is the central difference scheme. Right, and so for central difference, we're going to approximate just a little bit more quickly. Okay? So what I'm going to do is I'm going to take the Taylor series representation of yi plus 1 and yi minus 1 and subtract. Right, so we have yi plus 1 minus yi minus 1. Okay. And so, I'm going to go a little bit faster just for the sake of time. Okay, but we're going to have a difference here of yi minus yi, so that's going to cancel out. Okay. Then we have the first derivative term, so we have du dx, or excuse me, dy dx, dy dx times delta x minus a negative delta x, okay, plus d squared y dx squared times a 1/2 delta x squared minus delta x squared, okay. And then we'll do one more term, e cubed y dx cubed times delta x cubed over 6 minus or plus delta x cubed divided by 6. Okay. All right, so basically we're taking our first two and then subtracting. Question?
There's second term minus the negative as well.
Yes. Yeah. Oh, no, this one's just a straight up minus. Yeah. That's where you get the extra accuracy for central difference, because that first error term is actually going to cancel out each other. Yeah. Mhm. Kind of the beauty of the central difference scheme is that you basically take the leading error terms for both forward and backward difference, and you just kind of subtract them from each other and they cancel out. And so to simplify this, we have yi plus 1 minus yi minus 1 is equal to dy dx times 2 delta x. That next term there is going to cancel out. And so we have d cubed y over dx cubed delta x cubed divided by 3. Okay. I'm going to divide both sides by 2 delta x. If we do that, we have yi plus 1 minus yi minus 1 divided by 2 delta x is equal to dy dx plus d cubed y dx cubed delta x squared divided by 6. Okay. All right, and so through all that algebra, we of course end up with our central difference scheme, which is our derivative is equal to our right neighbor minus our left neighbor divided by 2 delta x. Okay. And then everything after that is our leading error term. Okay. Of course, there's more error terms after this as well, but we only care about the leading one. Okay. And of course, the thing that stands out about our leading error term is our grid spacing. Okay. And so unlike the forward difference and the backward difference, our leading error term here scales with delta x squared. Okay. And so what this tells us is that the central difference scheme is second order accurate. Which is better than first order. All right, any questions on this? Okay. So that is our our 3 methods. Okay. And so let's dive a little bit deeper into to talk about what it means to actually be first order or second order accurate, and why is it better for it to be second order accurate. And so for first order accuracy, this tells us that our error scales linearly with the grid spacing. Okay. And so this basically tells us that the amount, basically the amount that we reduce our grid spacing by, we can expect our error to shrink by that same amount. Okay. And so kind of the example that I always like to give is that if you cut your grid spacing in half, Okay, and so you make your grid kind of twice as small, then you're also going to expect your error to be reduced by half as well. Okay, for first order accuracy. Okay. For second order accuracy, because our error term is delta x squared, that means our error is going to shrink faster than the amount that we shrink our grid space. Okay. And so if we go by the same example that we did, in the previous statement, hey, if we reduce our grid spacing by half, our error is not going to be reduced by half. It's actually going to be reduced by a factor of 4. Okay. Right? Because remember, for second order accuracy, what we say is that the error scales with delta x squared. And so if we did delta x squared, we did delta x divided by 2 squared. Okay, that means our error is delta x squared divided by 4. And so that's why our error is reduced by a factor of 4. Okay? And so the higher order accuracy that you can obtain in a method, the better. That just means your results are going to scale with the grid spacing a lot better. Okay? I will say though that for most in the world of kind of practical computations, if you can achieve second order accuracy is usually really, really good. There are ways that you could increase the accuracy. I think later in the class we'll talk about third order, fourth order accurate methods. And there are some situations where you would want to get up to that level. But a lot of times, what we like to say is like the juice is not worth the squeeze. And so when you start getting into these third order, fourth order, fifth order methods, it tends to become a lot more complicated because you need to involve a lot more neighbors. And so that actually complicates your algorithm quite a bit. And so it becomes not really worth it. So usually if you can obtain second order accuracy, that's usually pretty good. And that's a pretty good code that you create. Okay. All right. Any questions on this? Okay, so a couple more, one more thing that I want to go over before we move on to the next big topic, which is derivatives in 2 dimensions. We're probably not going to do any 2D problems until next week, but since we're on the topic of finite differences, I did want to let you know that you can apply finite differences in 2D as well. Okay? And so we're going to be doing a lot of problems in this class where we work on 2-dimensional grid. Okay. And so it's going to look like this. Okay, so we have a square, in this case, a square grid. And so let's say, we're considering this point right here, okay? And this point has its 4 neighbors. And so it has a neighbor on the north, a neighbor on the south, a neighbor on the east, a neighbor on the west, okay? And so the way that we usually denote this, we're going to use the same kind of notation, kind of the generic notation. What we say is that this location is at location I comma j, okay? where I is some arbitrary index in the x direction and j is some arbitrary index in the y direction. Okay. And then based on this, we can label all the neighbors as well. And so the north neighbor will be I comma j plus 1. Okay. The east neighbor is going to be I plus 1 comma j. Left neighbor is going to be I minus 1 comma j. And the south neighbor is I j minus 1. Okay. So relative to our point of interest here, I comma j, then we can characterize all the neighbors as well. And so in 2 dimensions here, I'm going to switch variable names just because I'm using x and y for the directions now. And so what we can say is that if we had some kind of function u on this grid, okay, and so u is a function of x and y, then we can compute its derivatives. Okay, so we have partial u partial x. Okay, this of course is going to be equal to, if we use our usual central difference scheme, it's going to be the east neighbor minus the west neighbor divided by delta x. 2 delta x. Okay, so this is going to be u I plus 1 comma j minus u I minus 1 comma j all divided by 2 delta x. Okay, we can do partial u partial y as well. Okay, and so if we're going to take the derivative in the y direction, that means we need the north neighbor and the south. Okay, so it's going to be u I j plus 1 minus u I j minus 1. Okay. And we're going to divide by the grid spacing in the y direction. So it's going to be 2 delta y. Probably starting next week, we'll probably go over 2D stuff. I think this week we're just going to focus on just 1D. All right. Any questions on this? Oh, one more thing I forgot before we move on to diffusion. We need this actually for diffusion is second order derivatives. Okay. And so finite difference is not just limited to first order derivatives. You can do it for second order derivatives as well. Okay. And for second order, it starts to get a little bit more complicated. There are a lot of different schemes that you can do for this one. There is a forward difference, backward difference. There's higher order schemes as well. But just for the sake of simplicity, we're going to stick to just one scheme for second order derivatives. Okay. We have d squared y dx squared. Okay. The finite difference approximation for this is going to be y plus 1 minus 2 yi plus yi minus 1, all divided by delta x squared. Technically speaking, this is a central difference scheme for the second order derivative. This scheme is second order accurate. And so just be a little bit careful because I use the term order quite a bit. And so there's the order of the derivative. Okay. And there's also the order of accuracy of the finite difference. Okay. So it's it's unfortunate that we use the same term for both, but try to kind of keep them. Okay. All right, any questions on this? 2D and second order derivatives here. All right, and so that's, the introduction to finite differences. And so, we're going to be working with these for the next few weeks. Okay, so basically, whenever you see a derivative, we're going to be replacing with the finite difference just to make our lives a little bit easier. Okay. All right, so let's actually, start to apply this to some problems. Okay. And so we're going to go back to, if you remember from our, our review of heat transfer, we went over that general conservation equation, right? So we're going to go back to that, and we're going to see how we can apply finite differences to actually solve that equation. Okay. So let's do 1D fusion. Finite differences. Okay. So we're now ready, now that we know finite differences, we've known it for less than a week, we are ready to use it to solve problems, okay? All right, so let's start by recalling our general conservation equation, right? So remember, we use this equation, it can be used to represent heat transfer, so it's a form of the heat equation, but we can also use it for mass transfer and even for fluids, okay? So our general conservation equation, we had partial phi partial t plus u partial phi partial x plus phi partial y is equal to gamma partial squared phi partial x squared plus partial squared phi partial y squared plus q. So if you recall this term here, which is the time derivative, this is our unsteady term. These two are our convection terms. These are the diffusion. And this here is the source. So that's our full equation. And so, our goal is going to be to solve this whole thing, okay? And we will. And so we are going to reach a point where we're going to solve everything here together. But of course, right now it's kind of a little bit too much to deal with that at once, okay? And so kind of the approach that we're going to take over the next few weeks is that, we're going to be building up this equation, starting from like its very basics, so for kind of its simplest form, and then kind of adding some complexity on top of that from the week after. Okay. All right. So with that said, we're going to eliminate a lot of these terms. Okay. And so just, you can kind of, maybe you can guess kind of what we're going to start with here, just based on the title of this section. And so we're going to start with just simple 1D diffusion. And so that means we're going to assume steady state. Okay. So if we assume steady state, then the unsteady term goes away. We're going to assume that there's no convection, and so convection is also going to go away. And additionally, we're going to assume that it's 1D. Okay. And so by 1D, we eliminate any derivatives with respect to 1. And so through some assumptions, we are going to get rid of most of the terms just to make our lives a bit easier. We're going to leave the source in there just because the source is kind of what makes things a little bit interesting. Okay. And so if we eliminate all this, we're left with 0 is equal to gamma times d squared phi dx squared plus q. And so you'll notice I changed the partial derivatives to just the regular derivative because we just have one dimension. Okay, so we're not considering the y direction, we're only considering x, and so we can thus use kind of a regular derivative. And so what we're going to do is that we're going to apply finite differences to this and kind of come up with the ways that we can solve this using finite differences. And then more importantly, on Wednesday, we'll see how that translates into code. And there's a reason, kind of another reason why I'm starting with this as well, is that because this equation here is so simple, we can actually find exact solutions to this as well. And so we can actually solve a lot of these problems by hand and use those to actually check our solutions. Okay? And so whenever you're developing a computational code, whenever you're developing a solver, it's always important to work with problems that you kind of know the solutions of. Basically, problems that you can find the solution of the way, just so that you can check your work. Okay. Because what you'll see soon is that when you're developing these codes, there's kind of a lot of things going on at the same time, especially if you're kind of learning MATLAB kind of the first time as well. And so you want to work with kind of problems that you know so that you have a way to check your solutions. Okay, so that's kind of the reason why we're kind of starting this as well. All right. Any questions on this? Okay. All right. So actually, let's start there. So actually, let's do an example where we can solve this exactly. All right. We're going to have a relatively simple equation here. And so it's basically going to be a second order equation. So we have d squared phi dx squared is equal to 6x. Okay. So our source term here is a minus 6x. And then I just moved it to the other side of the equation. So it just becomes a positive 6x. Okay. Since we have a second order derivative here, we have a second order ODE. And so the boundary conditions that we need two boundary conditions to solve this. Okay. So we're going to have a boundary condition on phi. So we're going to say that phi of 0 is equal to 1. Okay. Our other boundary condition is going to be a boundary condition on the derivative, where we say d phi dx at x is equal to 1 is equal to 0. Okay. So let's solve for the exact solution to this problem. All right, so the good thing about this problem is that it's we can solve it just through direct integration, right? And so we have that the second order derivative of phi is equal to 6x, okay? And so if we want to solve for our solution here, phi of x, then we just have to integrate this, okay? write it again. So we have d squared phi dx squared equal to 6x. Okay. Let me integrate both sides. Okay. And so if we integrate the left-hand side, you just end up with d phi dx. Okay. We integrate the right-hand side, we're taking integral of 6x. The integral of 6x is going to be 3x squared. Okay. But remember, if you kind of think back to 308 or your differential equations class, whenever you perform an indefinite integral like this, or basically an integral without any integration bounds, we have to add an arbitrary constant. Okay? So the C1 here is an arbitrary constant. Remember, the reason we do that is because, since we don't have any bounds, that term would naturally go away if you took the derivative, right? And so if you kind of reverse this process, and you took the derivative of this function, then that C1 would go away because it's just kind of just an arbitrary constant. Okay, okay, so let's integrate this again. And so if we integrate this again, on the left-hand side, we get phi of x. Okay. And then on the right-hand side, we integrate 3x squared. That's simply just going to be x cubed. Okay. We take the integral of C1. Integral of C1 is going to be C1x. And then just like we did in the previous step, because we're doing an indefinite integral, have to add an arbitrary constant. Right, so that there is our general solution. So our general solution to this differential equation right now is x cubed plus C1x plus C2. Okay. So our next step is going to be to apply our boundary conditions. Okay. Our next step is to apply our boundary conditions to solve for C1 and C2. Okay. But any questions on anything that we covered up to this point in this example? All right, so far this is just kind of simple, just straight up integration. Okay, so let's apply the boundary conditions, and let's take a moment to kind of describe our boundary conditions a little bit more carefully as well. Okay, and so our first boundary condition, let me go ahead and write it down again. Our first boundary condition stated that phi of 0 is equal to 1. Okay, so let me kind of describe this kind of boundary conditions in words, just so that you can kind of see what it means, because this pattern is going to show up again quite a bit in this class. Okay? And so another way that we can describe this boundary conditions is that we're kind of forcing, or we're specifying the value of our solution at a specific location. Okay? So this is kind of as direct of a boundary condition that you can have. And so we have our solution phi of x, and so what this boundary condition states that when x is equal to a certain value, then phi must be a certain value as well. Okay. So these types of boundary conditions where you directly specify the value of the solution at a location, these are often called Dirichlet boundary conditions. So we'll see boundary conditions like this later on. And you know, the reason I'm kind of specifying it, the reason we're kind of categorizing it is because once we get to the computational section, you know, once we solve this with code, basically, the way we code up Dirichlet boundary conditions is going to be different than the way we code up Neumann boundary conditions. So, you know, we're kind of making the distinction now so that, you know, once we get to the coding part, you know, it kind of becomes clear why we do the code one way versus. So before I get into the other boundary condition, let's go ahead and apply this. Okay. And so if we apply this boundary conditions, we have phi of 0. Okay. And so I'm going to take our general solution here and plug in x is equal to 0. Okay, so we have 0 cubed plus c1 times 0 plus c2. Okay. And this boundary condition states that this is going to be equal to 1. All right. Excuse me. Of course, everything with 0 here is going to cancel out. 0 cubed is 0. C1 times 0 is 0. And so this tells us that C1 is equal to 1. Okay. And so our other boundary condition that states that d phi dx at x is equal to 1 is equal to 0. Okay. But the way we're going to characterize it is that this is a condition, or this is a specification on the derivative of the solution. Okay. So, you know, we have a condition on the derivative. And so whenever you're specifying a condition on the derivative, we often call these Neumann boundary conditions. In truth, you know, Neumann boundary conditions actually encompasses a lot more than just derivatives. But for the context of this class, we're going to mostly refer to derivative conditions as Neumann boundary conditions. Okay, so let's go ahead and apply this. And so first we need to take the derivative. So d phi dx is equal to 3x squared plus c1. Okay. And so if we apply this, so d phi dx at x is equal to 1 is equal to 3 times 1 squared plus c1. Okay. And according to the boundary condition, this is going to be equal to 0. And so we solve for c1. We subtract 3 from both sides. So this tells us that c1 is equal to -3. All right. And so we go ahead and apply this to our solution. So we have phi of x is equal to x cubed x cubed minus 3x plus 1. That is our final solution. All right, and so let me plot this just so that you have in your notes, so that when we write our code on Wednesday, you have something to compare it to. Okay. So if we plot our solution, and so the horizontal axis here would be x, the vertical axis would be phi. Okay, and so our solution here is going to start at 1, and then it's going to kind of decay down, kind of like that. and kind of asymptotes around from -1. All right, any questions on this? All right, let's stop here for today. So because the next thing we're going to do is we're going to basically redo that same example, but we're going to solve it with finite differences. Okay. And so, so on Wednesday, we're going to do our lecture kind of in 2 parts. And so in the first part, I'll kind of show you by hand how you would solve this with finite differences. And then in the second half of the lecture on Wednesday, we'll see how that actually translates into code. Okay. All right, and so that's it for today. And so remember, homework 1 is due tonight. So, make sure you kind of finish that up and submit it for the deadline. Okay. And then homework 2, I'm working on your homework 2 right now. I think I'll have it posted by Wednesday. Okay. All right, so thank you everyone for coming today. Hope you have a good evening, and I will see you on Wednesday.
Both very stuck on 3.
Okay.
Very stuck.
Yeah, this one, yeah, that one always kind of trips people up. Yeah, so this one, so the thought process for this one is actually really different than what we did in class. So, we have a matrix, right? So normally, we talked last week about a matrix. Normally you want a message form. But in this case, I only gave you one formula, right? So the formula only goes. So if you kind of read the hint, so the hint is kind of, we have this for loop, but that for loop is only going to visit each of the rows. Okay? And the reason for that is that if you kind of look back up to the output here, we're setting values here on each row here, but they kind of all follow the same pattern. Right? So we have kind of this cluster of loops. So you have a -2 on the diagonal.
Yeah, I kind of got that it's, I think what we're trying to do is basically tell the thing that when there's a 2, if there's a space next to it, that space is 1.
Correct. Yes.
Right. So that's what we're trying to do, right?
Exactly.
If it's a -2, then there's a 1 next. The location of the -2.
Exactly. So the -2 is actually always in the same place. It's always on the diagonal. And so I'll give you a hint. So this is kind of where the -2 gets set.
Okay.
Because this happens with this for you by visiting row 1 or 2. And the -2 happens every single time. Who are you? So what you can say here is remember this for loop is going to go from I or from index. That's where. And so we say B at index from index. Right. That's going to give you. That's going to equal to -2. You're still using the, but you are hard coding the -2.
But then the 2 will depend on what the ones depend on what the 2 is.
That's true, but the ones will also depend on which row they choose. So if you look at the middle 3 rows, the middle 3 rows have 1 on the left and the right.
Right.
Where the 2 is. You know where the 2 is going to be. The 2 is going to be on the diagonal. And so what you can say is the left neighbor is going to be B at index -1, (1), or index -1, index. And the right neighbor is index +1, index, right? And so if you kind of use that, kind of notation, and then you use the if statements here to kind of keep track of what you're doing. And so let's say that this first if statement is for one of the first row. The first row is different because there's no left neighbor, but there is a right neighbor. And so if you're in the first row, then maybe you can set the right neighbor. And you say else if, maybe you're in the last row. So if you're in the last row, maybe you just set the left neighbor. But in all other cases, if you're not in the first row or the last row, exactly right.
We're just array addressing session?
Exactly. Yeah. That's why we do this. It's for practice. This one's a good one. This one's an important one too, because you'll see on Wednesday when we actually write the code for diffusion. We're actually gonna have this exact pattern. No. That's kind of most of the time.
So like you said, 4 is input index 1 to 5.
Yeah.
Now that how do you call? You would just put 1.
Exactly. Yeah. So the matrix number will get 2. The first one is
The address first and the last one.
So the first and last row are kind of special. And so in the first row, you just have a right number, and the last row you just have a red.
The recruiter for
so the
the
F
call
is the
Sydney
first
this
one,
morning.
Yeah.
and
And
then
basically said that
the
they
house
actually
fifth
performed
is the
really well.
and then the else is the last one.
And also.
Flip that around. So LSIF will be the last. Well, you can set it like this.
Basically, they
So
say.
LSIF, you're in the table.
Yeah,
But then it would change the
basically-
photo.
basically saying-
Remember for the middle rows, you have to do 2 assignments.
Oh, I see, I see. Oh,
Yes.
You
yeah,
can do
what
that.
of
too.
them had 2 cents, okay.
Yeah.
That's it.
So will we just change the index for when there's 2 assignments?
You can do that. Yeah.
Okay,
Okay. Hey,
Yeah.
thank you.